Question 16, hydrogen peroxide solution H2O2 is catalytically decomposed by manganese oxide, and the equation for this is 2H2O2 would decompose to form oxygen gas and 2H2O. Okay, so to study the effect of the concentration of hydrogen peroxide solution on the rate of decomposition, the total volume of oxygen gas involved was recorded against time, and 3 experiments were performed using a fixed mass of catalyst, but with 3 different solutions of hydrogen peroxide. Now, when it comes to speed of reaction graph questions, there are 2 aspects that we will take note of. The first one is the maximum volume of gas produced. Okay, so all these are the maximum volume of gas produced, and this depends on the number of moles of limiting reagent. So what do I mean by this? If experiment 1 has 1 mole of limiting reagent and it produces 10 cm³ of gas, and experiment 2, okay, it has twice the number of moles of limiting reagent, I would also expect that the maximum volume of gas would also be twice at 20 cm³. Okay, so this is the first aspect. The second aspect is on the gradient of the curve, which tells you the speed of reaction. So a steeper gradient would indicate a faster speed of reaction, while a gentle gradient would indicate a slower speed of reaction. Okay, so with that, we are going to focus on the first aspect, the maximum volume of gas produced, that depends on the number of moles of limiting reagent. So we have to identify the limiting reagent in this reaction. In this case, since there is only one reactant, H2O2, this would be the limiting reagent. Okay, so now my next step, I will go and calculate the number of moles of H2O2 for all 3 solutions. So the formula that I'm using here would be volume times concentration, whereby volume is in dm³, concentration is in moles per dm³. So for solution 1, to find the number of moles of H2O2, okay, I have 15 cm³, so 15 over 1000 dm³ times 2 moles per dm³. That will give you 0.03 moles. Okay, so I'm going to write here at the side. And for solution 2, 30 over 1000 dm³ times 1 mole per dm³. This would also give you 0.03 moles. And finally, for solution 3, okay, 30 over 1000 times 2 moles per dm³, that will give you 0.06 moles. So if you look at solution 1 and 2, you realize that they both have the same number of moles of limiting reagent of H2O2, which means that the maximum volume of gas produced for solution 1 and 2 is also the same. Okay, so when you look at these 3 curves, X, Y, and Z, I can deduce that Y and Z, they belong to solution 1 and 2 because they have the same maximum volume of gas evolved. Okay, and if you look at solution 3, 0.06 moles, this has twice the number of moles of limiting reagent than solution 1 and 2. So this means that the maximum volume of gas produced would also be twice compared to solution 1 and 2. Okay, and so curve X, since the maximum volume is twice compared to Y and Z, this must correspond to solution 3. Okay, so straight away you know that curve X is solution 3, which means I will know that the answer is option C. Okay, but between solution 1 and 2, let's identify. So first aspect is done. Now I'm going to be focusing on the gradient, the speed of reaction. And the factor that I'm going to be focusing on would be on concentration. So I'm going to compare the concentration of solution 1 and 2. Solution 1 has a higher concentration. okay, compared to solution 2. So this means a faster speed of reaction, and it will be represented by a steeper gradient. So if I compare the gradients between curve y and z, okay, this is the gradient. Curve y has a steeper gradient, which means it has a faster speed of reaction. So curve y, it will correspond to solution 1, while curve z corresponds to solution 2 with the lower concentration, slower speed of reaction, so it will have a more gentle gradient. Okay, so answer for question 16, it will be option C.